Can start. So welcome everybody to our weekly colloquium. Today is a great pleasure to have Rafael Chaves. So let me introduce a bit our speaker. So he is currently the leader of the Quantum Information Research Group in IIP in Natal, and he's also deputy director of the same institute. So in his career, he attracted many grants, for example, from the Serra Pileira Institute, from the Templeton Foundation, and also from the Simons Foundation. And his research is quite broad in quantum information, and particularly work on causality theory, machine learning, and he has also a focus on experimental implementation of quantum information principles and protocols. And today's talk will be about quantum causality, rethinking cause and effect. Rafael, the floor is yours.
Thank you. Well, so let me start thanking ICTP and Celso there for the opportunity to talk here. So I've been told that the audience is quite broad, not only people from school, but also from ICTP. So I really tried to make a very broad and non-technical talk. You can interrupt me at any point, okay, if something is not clear. So let me just tell you where I come from, or where I'm based now. Is the International Institute of Physics. It's a kind of broader institution to ICTP. We actually have formal agreements, and the idea is kind of the same, like research on theoretical physics, like a lot of events and so on. So we don't have FAPESP, but we have nice landscapes, so it's also attractive. So here's the research group, Quantum Information and Quantum Matter. It's me and Rodrigo, who is the quantum matter expert in the group. And so like students, postdocs, visitors, here are some of the events we have organized in the last years. Okay, so what's the talk about? You can see, like, from a broad perspective as what you can learn at the interface between two very different Nobel Prizes, one in economics, 2021, in particular the one given to these two gentlemen here on their study of causal relationships, or like causality theory, and the Nobel Prize in Physics 2022, given to the violation of Barrow inequalities, like the experimental proof of quantum entanglement. So that's the basic guideline that we are going to follow. And to show what we can learn here at this interface, I'm not going to go through all of that, it's going to be impossible, but I will start with a crash course on causality theory, classical causality theory, then apply that to a very simple, very famous quantum experiment, the so-called double-slit experiment. And I was very happy, like some years ago, because applying causality theory to this very simple experiment, I allowed myself to disagree with Feynman, so it's not every day that you can do that, right? Then we are going to see, like, Bell's theorem, that it's the topic of the Nobel Prize some years ago, but from this causality perspective. Post-quantum I'm going to skip, and then end, like, talking a little bit about how you quantify causality in a classical and also in a quantum setting with some applications. Okay, so a crash course on causality. If you look at the internet, you're going to see many pictures like that. It's not difficult to find. Here, in the particular case of ice cream and some different tragedies. So if you plot, like, the number of ice cream sales and shark attacks or other things here, the function of the month in the year, like from December to November, you see almost perfect correlations between with shark attacks. Here it's violent crime index, here it's forest fires, here drowning deaths. And of course, you see this peak here that in the northern hemisphere, it's like summer. Well, don't blame the ice cream. Of course, we know what's going on here, as the statisticians would certainly not let us forget. Correlation does not imply causation, so of course, it's not the ice cream that is causing any of these tragedies. It's the fact that they have a common cause. In this case, the hot weather. So more people are in the streets, more bad things happen, and of course it's hot, so they want to have ice cream. Okay, so this is very simple, like in hindsight this is trivial, but I think the crucial point, and that I'm going to defend here, like in favor of causality theory, is that this idea has gone too far, and like even in, I think this was in 2008, there is this paper in Wired where the author says things like this. Correlation supersedes causation. Science can advance without any models, theories, anything. Correlation is enough. Just stop looking for models, throw the numbers in the biggest computer centers we've ever seen, and let the algorithms find patterns where science cannot. So if this would be true, it would be the end of our jobs. Luckily, this is not the case, and I like a lot this paper here from 2016, where basically they took a lot of different databases, and what they found was the following. Very large databases, they contain arbitrary correlations, and these, they appear not only, not because of the nature of the data, just because of this size. So most correlations are spurious. Too much information tend to behave like very little information. So of course, the scientific method can be enriched, but not replaced by machine learning. And here are two figures that I like. If you would just like blindly look at correlations, soon we would be eating chihuahuas and using these rugged dogs after a shower, right? So of course we have to go beyond that. So here's just another plot. Well, he's actually doing good movies now, so maybe this will change soon. But yeah, the point is that if we look enough, we are always going to find patterns where there is only noise. And the point here is that we cannot just take a mountain of data and try to find something. We are always going to find something. In science, we do the opposite, right? We cannot interpret data in a theoretical vacuum. Typically, we start with a hypothesis, and from this hypothesis, we are going to design some experiment that is either going to confirm it or to falsify it. So basic stuff, but the problem here is how should we start? Because this is a bit of a circular argument. To get hypothesis, I should get data, but to really interpret this data, I should start with a hypothesis. So how I'm going to stop that? And that's one of the reasons why causality theory has been introduced end of the 80s, beginning of the 90s in the context of artificial intelligence. But since then, it took over like many different fields, so like medicine, biology, statistics, machine learning, of course, psychology, and more recently, even quantum physics. Like in the last 10 years, there is this new field that it's what we call quantum causality. Okay, so that's like the motivation for causality theory, but let's see how this works in practice. So let's start simple. It's what we call the Heisenberg's principle that goes against this mantra in statistics. So basically, well, the statisticians would say correlation does not imply causation. Heisenberg will say, well, that's not really the case. There is no correlation without causation. Or perhaps in less vague terms, it say that if an improbable coincidence has occurred, there must exist either a direct influence and or a common cause between these apparent coincidences. So an example, let's say I was here during this week. I would sit there outside to drink a coffee and look to different rooms. And always when I look at these two rooms, these two offices, either the lamps on them would be on or off, on, off, always on and off. So a perfect correlation between these two light bulbs. Seems quite unlikely that always people would leave and enter these rooms at the same time. There must exist some sort of causation involved here, and it could be of two kinds. Direct influence, so like because of some bad wiring in the wall, whenever I turn off or on one lamp, this causes the lamp in the other room to be fine. Or it could be to be on or off, or it could be that the wires are fine, and what's going on is that you have an L instead of the previous concessionária, and there is some short circuit happening somewhere, what would explain why the lamps are on and off at the same time. So that's the basic setup. I would say this is like the basic aim of a good machine learning pipeline, that not only you want to learn something from the correlations of the data, but also learn causal relationships, what it's causing what. So we could think of a machine, a robot, or something that has sensors. It's going to observe the world, like its environment, lamps on and off, and from these observations want to know what's causing what. And it's important to say that some of the data is going to be empirical in the sense I can see if the lamps are on or off, but there are some other variables that might be important for my model that I just cannot observe. I don't know if there is a short circuit happening somewhere outside, right? So I have to treat this as a latent factor, or like connecting this with Bell's theorem, I have to treat this as a hidden variable. Okay, so how we do that in practice? There are different ways. I'm going to use here one that it's very common these days, that it's these DAGs, or directed acyclic graph. So I have nodes. Each of these nodes is going to represent a variable. And these variables are interconnected by these directed edges that basically carry information about causation. In the classical case, without loss of generality, I can always assume that a given node in my DAG, in my graph, is going to be a deterministic function of its graph theoretical parents plus some local noise. So what I'm saying is that, well, A is going to be a function of lambda 1 and lambda 2 plus some local noise that will affect only the variable A. Okay, so I use these DAGs, and the crucial realization, so here's the father of causality theory, Judah Pearl, a very famous book of him. I recommend everyone to read it. But basically, what was realized is that the causal relationships that a given causal structure, a given DAG imply, they are encoded in the conditional independencies that are implied by a given graph. So what this means, let's look at these two variables here, lambda 1 and lambda 2. They do not have an arrow from one to the other. Neither there is a third node, like lambda 3, that acts as a common cause between both of them. So these two variables should be causally disconnected, and if there is no causation, Reichenbach's principle, they should also not have any correlations. So this means that whatever is the physical, chemical, biological mechanism that operates in these two variables, the probability distribution that governs them should factorize, right? They should be statistically independent. Another kind of conditional independence, it's something like this. So A and B, they are correlated because they have a common cause, lambda 1. But if I condition on lambda 1, these correlations, they should be screened off, right? I'm basically like putting out the source of correlations between these two guys. And that's it, like conditional independencies, they hold information about the causation. So how I use this in practice. Now, I'm not going to tell you where I can get the hypothesis from. This is more complicated, but let's assume I have a hypothesis, but now I have a way of checking if that's true or not. So let's say that I have data about 6 variables, lambda 1, 2, 3, A, B, C, and for some reason I have a hypothesis that the underlying causal structure that governs these 6 variables, it's something like this. How can I confirm or falsify that? I basically list all the conditional independencies. Here, it's only 2 that are implied by this DAG, and I check each of them. If one of them is not valid in my data, I can be sure that this data is incompatible with this hypothesis. I just proved my model to be false, okay? That's very nice. The problem, and this is how we connect this with quantum physics. In most cases, we don't have access.
Question.
Yeah.
Sorry, can you go back one slide? You said that those are the only assumptions for that model?
No, I'm...
That is a specific...
Yeah,
okay.
yes. There are many more. Like, we have efficient algorithms to list all these conditional independencies. There can be, like, exponentially many of them, but we know how to list them. But if this would be the end of the story, I mean, very simple, nothing to do. But in practice, we don't have access to all the variables that we want to test, right? So like in this case, let's say that I have these 3 variables here that I do not have access. So I presume they exist. I presume that they have a well-defined probability distribution. This is important when we talk about quantum stuff. But I do not have access to them. So I have to trace out them from my description. And this is a well-studied problem in algebraic geometry. It's what we call quantifier elimination. So basically, I have a global object that is constrained by some polynomial equations, and I want to trace out some of the variables from my system. And when I do that, I typically will get like polynomial inequalities, like nonlinear inequalities that will describe the region in probability space where the probabilities are compatible with such causal structure. So this is going to become clear when we go to Bell's theorem. But yeah, basically like anything that is compatible with this model at the level of the observable variables A, B, and C should be decomposable in such a way where you see here B is a function only of lambda 1 and lambda 3, and lambda 1, 2, and 3, they are independent among them. So like this representation here like encodes these causal assumptions, okay?
So, just, I wanted to ask before, but now I think I understand. Let's say you are treating on a different footing, let's say square versus circle, because circles are the one that you can keep track.
Are my lamps on and off?
Okay, and lambda 1, lambda 2 are
the short
things
circuits.
that, okay.
Yes. And the role of this in quantum physics is going to become clear in a second. Okay, so like basically I have to develop methods to like characterize regions in the probability space that are compatible with such causal structures. This problem has been fully solved in this paper here by Geiger and Meek in this uncertainty in artificial intelligence. But this problem is double exponential. So in practice, it means that if I have a causal model with more than 6 binary variables, I cannot solve anything anymore. So it's very hard in practice. So over the years, we had to develop many tools. I'm going to skip that for the moment and apply this simple framework to an even simpler setup that it's the double-slit experiment, okay? I think this will illustrate well the kind of questions that we can tackle with this causality theory. Okay, so just a motivation for that. Many years ago, like I was stuck in this idea of how we define non-classicality or quantumness or incompatibility with classical physics. Some people will say it's, well, I don't know, wave-particle duality, maybe it's tunneling, maybe it's the uncertainty principle. So I mean, there are many different ways you can choose to define what is non-classical for you, but I would like to have something that it's mathematically well defined, that you don't need to rely on words. And then the approach that we came up back then was the following idea. Well, if you can observe the same thing, replacing your quantum particles like ions or photons or whatever by ping-pong balls, then the phenomenon certainly is not quantum. Then the idea is that causality theory will tell us how to replace quantum particles by ping-pong balls. And we are going to do that in a mathematically rigorous way. Okay, so let's see how we do that in the double-slit. So I'm not going to read the whole phrase of Feynman, but he's basically saying that this double-slit experiment contains all the challenges or like the mysteries of quantum mechanics, and that's the thing that we will allow ourselves to disagree with Feynman. So what's this double-slit? Well, let's think here. I have a machine gun that spits like a single electrons. It could be any other particle here, but let's say it's electrons. They're going to travel. They pass through this double slit, like a screen with these two slits, and here they are going to be observed. So if I run this experiment, I'm going to see that when the electrons, they hit here the screen, they are going to let these small marks that are characteristic of a particle. But as the experiment goes on, we know that it's going to appear here interference pattern, that it's what we would expect from waves, right? So now we can say, well, what is interfering with what? Somehow, like many quotes, can it be that the electron is interfering with itself? It's passing through the two slits at the same time. Of course, this is not the case, but we can try to see the electron if he's really passing through the two slits, right? So we come here, we put a detector, and we try to see through which slit the electron is passing, and we are going to see that it passes either left or right, as we would expect. But when we do this observation, we change this pattern here, like this interference pattern is not there anymore. So when there is no one looking, it's like the electron is passing through the two slits. If we try to catch the photon, then he chooses one of the two slits, and we lose this interference. So, like, this is the famous wave-particle duality. And we can make this more interesting. So this was what Wheeler, that was the supervisor of Feynman, did, was to say, well, and if we decide whether we are going to observe through which slit the electron passed after the electron passed the two slits. So this is what we call delayed choice. We let the experiment run, and after we detected the photon, we decide if we want to know through which slit the through like the path information of this electron. Okay, so this is like there are many papers and experiments and arguments like around that, and even Feynman would say this is very quantum. There is no way we can try to interpret this in a classical setting. So let's see if this is possible. So this was the first thing that we tried to do, like after we learned about the causality theory. And what came out was very surprising, because it was the opposite of what we were expecting. So we did the theory, then soon after, many groups around the world did the experiment, and because it was so unexpected, like even Wired magazine wrote about the paper, and it's really simple. So let's go through a few steps here. So here's the double slit. The first thing I'm going to do is to map this to a photonic setup that it's easier to understand and to do experiments with, that it's a Mach-Zehnder interferometer. So now instead of electron, I have a photon. Instead of a double slit, I have a beam splitter that Zella was telling us earlier. So basically the photon, when he hits here, the beam splitter can pass either in this upper arm or in the lower arm. There is a phase difference between these two arms. And here I have my detection. So let's assume that this second beam splitter is not there. Then if the photon is coming here, he's going to hit here in the detector E. If it's coming here down, it's going to detect here, to be detected here in detector D. So this is what I would expect from a particle. It has a well-defined path. But if I put this second beam splitter, I'm erasing information about this path, and now what I'm going to see, it's like an interference pattern between these two detectors. Okay, so this is the double slit in a photonic version, and the next step is to put this in what we call in quantum information a prepare-measure scenario. So I have a preparation device that takes some input X, like a flip a coin or like a dice. It's going to decide which state is going to be prepared. So this preparation part would be this upper part here of my interferometer, and this X would change like these phases that I can imprint here in this upper part. Then I have my measure device, my measurement device that takes some input. For instance, it will decide whether the beam splitter will be present or not, and then I get an outcome that it's whether these two detectors will click. And you can see that a very simple underlying DAG causal structure that represents this prepare-measure scenario. It's something like this. I have a measurement, I have a preparation choice, X. It's going to prepare some state. If it's something that can be described classically, it's going to be a random variable, lambda. But I'm treating it here different because, well, I do not have access to this variable directly. The only access I have to this variable are the measurements that I do on it, right? And these measurement outcomes are D. Will depend, of course, on the state that I'm preparing, and it will depend on the kind of measurement that I'm doing. So whether I have the second beam splitter or not. Very simple, right? So we would expect, if the double slit is so quantum, that never I would be able to explain this quantum experiment with such a simple causal model. But to our surprise, this was not the case, and it's really simple. I'm not going to go through the details here. But the idea, or what we have to reproduce, is the following. So if the second beam splitter is not there, the wave function that I have just before the detection, it's something like this, right? 0, 1, meaning that the photon passed through this lower arm, plus 1, 0, with some phase that it's the phase imprinted here. So if I just measure these guys, I'm going to get with probability half, like either this detector clicking, or this one here, right, for this wave function, because the amplitude here is 1 over square root of 2. But if I put this second beam splitter, I'm going to see that I change the wave function just before I do this measurement, and now I see this cosine and sine that will give rise to this pattern here, that it's an interference pattern in the detectors. And here's like the classical model that I can come up with that explains this data. So what I'm saying here is the following, that if we give up this idea of wave-particle duality, or like these concepts that I sincerely don't know what they are just words for me, and I try to formalize in terms of like math, or in terms of causality theory, indeed, the double-slit experiment is a classical experiment. I'm not saying that Newtonian physics is going to explain it. I'm saying that there is a classical causal model, a well-defined one, that explains what we see in this experiment. But then, to make Feynman happy again, what we realized is that we could slightly change the experiment, and then we could get something that had no classical explanation. So now, instead of like putting in and out this second beam splitter, what I do now is that this second beam splitter is always present, but my measurement choice now, this Y here, it's whether I imprint a second phase just before the measurement or not. Right? So from the point of view of this causal structure, nothing's changing. I'm just saying, well, what I called Y before, that was this choice of putting or not the second beam splitter, now is basically the second beam splitter is always on, and I put an extra phase or not. And with this slight change in this setup, we now get something that it's non-classical. And how can we prove that? Well, we can always, when I have a causal structure, I can derive the set of compatible correlations with it. So this gives rise to Bell inequalities. And one of the Bell inequalities in this particular case is this inequality here. I'm not going to explain what is each of the terms here. But with quantum mechanics, we can violate this inequality. And this was what was done in these experiments. So showing that indeed, the delayed choice experiment can lead to non-classical correlations, but not in its usual form. We can connect this with three-throat causality, but we will not enter in this dangerous terrain here. Okay, so any questions up to this point? I'm going to change gears a little bit.
Just to clarify, the physical experiment that we really did was the one with light, right? No one with particles already.
It was with light, yes. But you could do with electrons, and as far as we know, it should be the same, yes.
Ask the question and then we repeat. You are too far.
No. Yes. So I'm theory agnostic, but I'm not. The classicality enters here in when I assume that this state that I'm preparing has well-defined values, like independently of me measuring this state or not. So the classicality assumption is entering in the nature of this variable here. In a quantum description, we would say this is a density matrix, wave function. Classically, we would say this is a random variable that has a well-defined probability distribution. So this is the notion of classicality, plus, of course, the causal structure that we are imposing to the experiment. So I'm fixing the causal structure to my experiment and imposing that the variables that I cannot observe, even if I cannot observe them, they have a well-defined probability distribution. So this is my notion of classicality. When you say no classicality, that means that at this point you would have to keep that. Yes, exactly. So in the second example, yes, but in the standard one, no.
So summarizing, you are saying that in the first example, a random variable can replace a quantum state.
Yes.
In the second example, a random variable cannot replace a quantum state.
Yes.
But now you mentioned something that confused me because you said that this is for this causal structure. So there could be another causal structure that maybe there's some variables that you haven't modeled just yet that could explain it classically.
Yes, so like I'm imposing this causal structure to my experiment. So I have my lab here, I'm preparing photons, these are sent through an interferometer, and there in front I'm like measuring something. So it's very reasonable that this is the causal structure that describes my experiment. So this is an assumption. I didn't want to talk about that, but now I have to. Retro causality. So you could say, well, but how can you be sure that this is the causal structure of your experiment? Then it's nice that you can prove that if you allow an extra arrow in your classical model, that it's this arrow here from y to lambda, you can indeed explain classically what's going on. But what is this arrow here? I'm basically saying that the measurement that I decide to do in the future is changing or has some causal effect on the state that I prepared in the past. And this is what Wheeler would like, actually. So what I'm saying is that, yeah, you can keep a classical notion as long as you give up like this idea that only the past can cause the future and not vice versa. But you see, this, at least to me, doesn't seem very plausible.
What about adding more hidden variables?
This will not help. Like, you can show actually that the only thing that could help you to explain classically what's going on is this arrow going backwards in time. Yes, you can do that. So you have a classical model, but it's one that it's a bit weird. Yeah.
Sorry if my question is too basic, but when you modeled classically the two-slit experiments with the probabilities, how is it different from the contextual approach to quantum mechanics?
Well, I would say that the contextual approach to quantum mechanics, it's a particular case of what I'm saying here. Like, so there are papers like from Eric Cavalcante, he's a Brazilian, but in Australia, he's based there. And basically, he put all these contextuality scenarios into this language of causal models. So I would say contextuality is just like, or non-contextuality in this case, it's like a particular case of what I'm talking here.
One of the great objections to retrocausality is the contextual aspect of experiments, which you cannot really give rise to counterfactual effects in this kind of experiments.
Well, but if you allow retrocausality, I mean, I think this was the reason why I didn't want to talk about it. But like, if you allow for retrocausality, you can do anything. So here's just like to say, well, you can keep it a classical interpretation, but you have to give up very basic assumptions. Yes, so this is an inequality that was introduced in 2010 in a paper of Tony Yassin from Barcelona in the context of dimension witnesses. So yeah, like, but here we use with a different, it's the same inequality, but here it's applied with a different idea.
To the CHSH, but at least the last term.
Yes. It's like, well, it's just because the CHSH is one inequality particular to a given causal structure. So yeah, like we are going to get to this point now. The Bell case or the CHSH case is just the tip of the iceberg. So there are many things. So it's not that this looks with CHSH, it's just that CHSH looks with a lot of other things. Okay, so let's look at Bell's theorem from this perspective. I will skip here this metaphysical part. Let's go directly here. Yeah, so here is the causal structure that I impose when I talk about Bell's theorem. I have Alice and Bob. They are far apart, so it's like a space-like separation scenario. Alice is going to receive some particle that it's produced here at the source, and the same for Bob. And notice here that I'm treating this variable as a hidden factor, right? Because in the case of like EPR and Bell, I want to know whether a hidden variable model can explain the predictions of quantum mechanics. So I treat the source. It could be a short circuit, it could be ping pong balls, or it could be entangled photons. I don't know. I just say, well, this there is a random variable that describes what's going on here at the source. And Alice is going to flip a coin, like heads or tails, and or 0, 1, and depending on this, the value of this coin, is going to measure some observable and get an outcome A. So, for instance, if it's the polarization of a photon, it could be measuring like the polarization in the vertical or the diagonal direction. And the same here for Bob. He has an input Y and gets an output B. So what is the kind of data that quantum mechanics allows us to treat? It's a probabilistic data. So what I get out of this experiment, it's the probability of getting some outcome A or B, given that Alice and Bob chose to measure observables labeled here by X and Y. Okay, so this is the kind of data I get from the experiment. The first assumption I have here is the classicality assumption, that it's to say that this hidden variable here exists and it has a well-defined probability distribution. So this is my notion of classicality. And the other assumptions are causal assumptions. The first is the free will or freedom of choice. That is basically saying that Alice and Bob, they can choose what they want to measure independently of each other and independently of lambda. So I can decide to measure a given physical system independently of the properties of this physical system. So it seems a good assumption, right? And the other assumption is, of course, the locality assumption, that because Alice and Bob are so far apart, like whatever is happening here in Alice's lab should not affect what Bob observed in his lab. Okay, so these are the three basic assumptions: realism or classicality, free will, and locality. And we know from the work of Bell that this gives rise to Bell inequalities. Actually, this inequality here was derived 5 years after by Clauser, Hoare, Shimoni, and Holtz. Clauser got the Nobel Prize in 2022. And this here, this here is a constraint that follows from these three basic assumptions: free will, locality, causal assumptions, plus the classicality assumption that this guy here has a well-defined probability distribution. But we know that if we put here quantum states, like entangled quantum states, we can violate this bound, reaching 2 square root of 2. So you see, like from this perspective, I didn't say anything about quantum mechanics. Well, now I said when I said that I can violate this with quantum entanglement. But the point is that from this causal perspective, this is basically a very simple causal inference problem. I have a hypothesis that it's this causal model here. Can this causal model explain the data that I generate in this experiment? And the answer, if I have quantum entanglement, is no. So from this perspective, the Nobel Prize 2022 is kind of simple, right? But simple things are also nice. Yeah, so here just a bit the math, right? I have here this causal structure. The conditional independencies that encode the causality assumptions here are just some of them. Here's the free will, basically saying that the probability of x, y, and lambda, they should factorize. Here is the locality assumption, that like whatever Alice is going to see in her lab should be independent of what Bob does in his lab. So but you see that all these conditional independencies, they depend explicitly on the variable lambda that I'm treating as a latent factor. So I have to eliminate this variable lambda from my description, and when I do that, I get exactly inequalities of this form here that explicitly do not depend anymore on the variable lambda. Geometrically, it's very simple to understand what's going on. So these sort of models, that it's what we call local hidden variable models, they define regions in the probability space that in this case are going to be polytopes, and the boundaries of this region here are exactly Bell inequalities. So what is a Bell inequality? It's the boundary of the region in probability space that it's compatible with my causal model, okay? And I can define quantum causal models, then I get something that it's a bit larger, but I'm not going to enter in these details here. Okay, so very simple from this causal perspective. So let's make things a bit more interesting. We skip this on the experiments. So let's go a bit beyond Bell. one way of going beyond Bell, so Bell, it's a bipartite scenario. I have an observable A1 here, A2 there. They have a source between them. They choose to measure different observables, and they get some data. And if they violate the Bell inequality, then they can be sure that the data that they are generating is incompatible with a given classical causal model. One thing we can do is now to go to 3, 4, 27 parties. So I have LS1, 2, 3, 4, and so on. And I have a single source that connects all of them. So, for example, this is what happens if I go to the JZ case. Now I have a tripartite or a four-partite state, an entangled state that is shared between all these nodes here. But I can do things that are much more interesting, and the inspiration for those typically can come from quantum networks. That it's the idea that now, instead of having a single source, what happens if I now assume that my causal structure involves not only a single source, but like independent sources of correlations. So when Zella talks about the rede Rio quântica, I think tomorrow or Friday, you are going to see that like if they start sharing entanglement between the nodes, they are not going to generate five-partite state, a JZ state, and share between the 5 nodes. They are going to have a source between UFI and UFRJ, another one between IME and CBPF, and so on and so forth. So it's very easy to generate bipartite states. Multipartite states can be very hard. So the idea, like in a typical quantum network, if you go like to these quantum networks in China, what they have is going to be something like this. So I have an entangled state between node 1 and 3, and another one between node 2 and 3. So now I have 2 sources, and it seems very natural that I assume these 2 sources to be independent. So I'm adding extra assumption here that it's the independence of the sources. And when I do that, a lot of new, very interesting phenomena arises. So I'm going to mention a few of them. From the experimental perspective. So in 2022, we did exactly this sort of network here. So in this network, it was in Rome, the Sapienza University. So here we have a quantum dot source of entanglement. One photon is coming here to the station A. The other one is sending in a free space link to this other station B here in the center. Here we have a different source of entanglement that it's based on a SPD C source. One comes here to the station C, and the other via a fiber link goes to this room here in the center. And the point of this experiment was 2. So the first was to show that we can combine hybrid technologies, both for the generation of the entangled states, but also for the transmission of these states. And the nice thing here is that if I would assume a causal structure of this kind, I could not violate any Bell inequality in this experiment here. So I could not detect the non-classicality of the data that I'm generating. But if instead I use the independence of the sources, we could indeed violate a Bell inequality. So you see here, this is illustrated in this figure. Here, it's what we call a bilocal hidden variable model. So I'm assuming, in this case, the independence of these 2 sources. I mean, they are in different buildings of the university. It seems fair to say that they are independent. And using these independence, I can violate this nonlinear Bell inequality here. But if I would not assume this independence, the inequality would be this thing here that I'm not violating, so this data would look classical. So when I start to look at these networks and take into account these independences, I refine the kind of things I can do, and it makes easier the life of the experimentalist to prove that it's generating some truly non-classical data. Here, it's another recent experiment, was done also in Rome. Now, it's the same thing, but with 4 different sources. So now it's what we call a star network, and it's obvious why. I have LS1, 2, 3, and 4, and here in the center, I have a central node Bob. So I have 4 sources of entanglement, and here's the same thing, but here it's even worse, right? So I get a point here. So what is this point? Are the correlations that I generate in this experiment. And I see that if I don't assume the independence of these sources, it's very far from violating a Bell inequality. But if I assume the independence of the sources, I can violate this other inequality here. So the idea of this experiment was really to go to this very extreme case and say, look, if you don't use this new sort of techniques, you are never going to see any known classical behavior, even in such a small network. And here is my favorite experiment so far. This was done last year. And here we look at a triangle network. So I have 3 nodes, Alice, Bob, and Charlie, and I have 3 sources now, one between Alice and Bob, the other between Bob and Charlie, and one between Bob and Charlie. And the nice thing here, that it's different from everything I said before, is that Alice, Bob, and Charlie, they always measure the same thing. Like in Bell's theorem, it's essential that Alice and Bob, they flip coins. So they have to flip coins and decide to measure incompatible observables in each run of the experiment. Otherwise, there is always going to be a classical model. But here, in this triangle scenario, we don't need that. Alice, Bob, and Charlie, they always measure the same thing. And even though they measure the same thing, we can still violate a Bell inequality. So where is the non-classicality coming from? From independence of the sources and from the fact now, so if we look here at Alice, she's receiving a photon from one source and another photon from another source. And now she's going to make a measurement that it's in an entangled basis. So we are replacing like this freedom of choice, this idea that they have to measure things, to measure different observables by this independence of the sources and the fact that they can make entangled measurements. Okay, so this we will skip. How many minutes I have more? Okay, so in 10 minutes I can finish that. This is the best part. It's the one that really keeps me awake at night. That it's how we quantify causality. So let's say I have 2 variables, A and B, smoking and cancer, lung cancer. And I clearly see from the data that they are correlated, right? Like people that smoked, they have a higher chance of having the disease. But how can I be sure that it's a direct causation and not some perhaps hidden factor that causes both of them to be correlated? So actually, this seems weird, but it was the answer of Marlboro in the 50s, right? To these sort of problems. But there are more recent problems, like so this is a paper from 2007, and they look at it in social networks, and what they observed was the following: that if you are a friend of an obese person, with time you are more likely to gain weight. And then the question was like, is obesity contagious? Something like this. Well, you become friend of this person here. This person eats a lot of chocolate cake, so you start eating chocolate cake, and you gain weight. This is one possibility. And the other is, well, actually the reason why you became friend of this person is because you both like to eat a lot of chocolate cake. So independently of becoming friend of this person, you would gain weight over time, right? So what we are trying to distinguish here, it's common causes from causal influences. And how can we do that? Well, we can't. We cannot distinguish these 2 things, at least if I look at the correlations between A and B. And the basic reason is that like a direct causal effect from A to B is indistinguishable. It generates the same set of possible correlations as this other model here, where I have a common cause, that it's not a directly observable common cause between A and B. Or like in general, I could have like a mixed model with these 2 things happening at the same time. But then what I can do, well, instead of doing passive observations, I can intervene in my system. So what would be an intervention? Instead of just observing A, I now force A to assume a value that it's under my control. So this is what we call doing, forcing A to assume a specific value. And in practice, what this does is a local change in my causal model, because if I force A to have a value that it's under my control, it's independent of any potential common cause lambda that it had with B. So P of B given A, this would be like observational data. P of B given that I intervene, I do A, these 2 things are different, and this naturally introduces a measure of causality. That, well, there are different ones. Here, we are going to focus on this ACE, that it's the so-called average causal effect. And you see, well, if A has no error to B, if I do A or I do A prime, the probability of B will not change. So this ACE is going to be equal to 0. But if I change A and I erase this error here from lambda to A, and I still see changes in B, well, then it's for sure that I have causation from A to B, and I can quantify that with this measure here. Okay, so what I'm saying is that if you want to know whether smoking causes cancer, I should take 2 groups, force one to smoke 2 packs of Marlboro every day for a few years and see what happens. Clearly, I cannot do that, right? So I have to come up with something more clever than just doing interventions. And that's the Nobel Prize of Economics in 2021, that it's, well, they were not the ones to invent, but they applied that for different economic settings, that it's what we call an instrumental variable. So it's an instrumental variable. I add a variable to my model, this variable x, and this variable x, it influences A, but does not directly influence B, and it's also assumed to be independent of these common causes between A and B. In this case of smoking, could be like the taxation of tobacco by the government. If the government makes cigarettes cost $100, less people are going to smoke, and if the zero is really there, we should see a decrease in the number of cases, right? And the opposite, if I make cigarettes free, everyone can smoke, and if the zero is really there, I should see an increase in the number of people with the disease. And the crucial thing, this was this seminal paper by Pearl and Balker, that was the PhD student of Pearl. They proved the following, and this is really deep and nice. Simply looking at the observational data, so I'm back to an observational data. It's the correlations between A and B, given that my instrumental variable, it's X. So the government tax more or less tobacco and see what happens. I'm not forcing anyone to do anything, right? But looking at this observational data, I can put bounds on what would have happened if I would force someone to smoke. So I can put bounds on interventional quantities using observational ones. So you cannot believe how this is used. Like every vaccine that we get out there passes through this test, like marketing campaigns to know if they are really successful or not. This is the sort of things that people use, like Spotify. They are using this now to know, or like variations of this thing to know whether a given recommendation that they give to you, it's successful or not. So you can imagine, like we want to know what would have happened if I did something without having to do it. So it's like a counterfactual reasoning, right? Okay, so all of that, it's for the classical case. So this bound here assumes that this common cause between Alice and Bob, it's a classical one. Then we said, okay, let's make things more interesting. So can we shake this with quantum mechanics? And the answer is, of course, yes. And I'm just going to give, so in this here, it's like the general theory for what happens in this case. And here it's one experiment that we did some years ago. So just to illustrate, like if I have a classical model, this bound here should be valid. The average causal effect from Alice to Bob should be bounded by this observational quantity here. But now, if the source between Alice and Bob is entangled state, funny things happen. So let's say that I have a maximally entangled state between Alice and Bob. There are 2 kinds of experiments I can do. I can just do observations. So Alice is going to measure some observable indexed by X and get an outcome A. And Bob is going to measure some P of M here that will depend on the outcome A of Alice and get an outcome B. So this is one important thing that I forgot to say. This is very different from a Bell scenario. In a Bell scenario, Alice and Bob are space-like separated. Here, I have a time-like scenario. Like Alice is doing something, she's getting an outcome, and this outcome will define what Bob will do in his lab. So now I have a temporal correlation. Okay, so Born's rule, like applied in this case, but the other thing I can do is to do an intervention in this quantum mechanical system. So what would be an intervention for Alice? Like if she would just do like her observations, she's receiving a photon and she's going to measure a photon like using some P of M. But now what she does is that she throws away this photon, she traces out this photon, she prepares a new quantum system, and then she measures this new quantum system. Effectively, what this does is to erase the correlations between Alice and the source that she shares with Bob. And now, it's not difficult to see that if Alice and Bob have a maximally entangled state between them, independently of what Alice does to her system, from the perspective of Bob, nothing is changing. Bob, in his side, what he has, if they share a maximally entangled state, it's identity over 2. So if Alice is doing, if Bob is doing projective measurement, independently of what Alice is telling Bob to do, the probability will be 1 over 2. So this means that the ACE is equal to 0. So this is a quantum mechanical calculation. I'm saying if I would do an intervention in this physical system, I would observe ACE equal to 0. But now I can say, but what, I can look at what the classical bound will tell me. And this classical bound will tell me that this ACE, for visibility high enough, this meaning that I need to have like a good entangled state. If the visibility of this entangled state, that it's this V here, it's high enough, this ACE is going to be strictly positive. So you see, the quantum causal theory is telling me that this ACE should be equal to 0. But the classical causality theory, it's telling me that it should be larger than 0. Okay? We did this experiment in 2018, and then after we did some refined versions. So let me only show you here like some experimental results. Here's the experimental setup. So here, these green points, it's the ACE that we observe in the system, in this quantum mechanical system, like this photonic setup, if we actually do the intervention. And you see that this intervention is very close to 0. And here, this curve here, it's what we should observe if this system would have a classical description. So we have a quantum mechanical ACE close to 0, and the classical prediction is saying that it should be larger than 0, so we have a violation of this bound, hence we are witnessing non-classicality, okay? I'm not going to talk about that, but more recently we've shown like applications of this framework into quantum computing. So like to quantify causality in quantum gates, in quantum circuits, or even in measurement-based quantum computation. This also has applications in randomness, so we can use this setup here to generate randomness and to certify randomness. And in some cases, we can have better certificates than we would get like from usual Bell tests. So it's not only foundations, but also like applications, like practical applications. We even thought of like doing a patent of this, but it was so complicated, we said, okay, let's just publish the paper and that's it. They should make our life easier, right? But they don't, so. Okay, so I come to the end of the talk. I think that if there is anything here you should take home, is that causality is a powerful, very general framework to treat any kind of data. So you can use this in Spotify for vaccines, but also to analyze problems in quantum mechanics. So through the causal lens, like this double-slit experiment, do have a classical explanation. Bell is a very particular instance of a causal inference problem, so we can generalize that for networks and many different scenarios. And I think like interventions that are this idea that instead of passively observing what happens in an experiment, I can locally change some parts of it. These are really very interesting. It's a really interesting tool, like with applications even in quantum computing. So these are the kind of things that we are very interested now in the group and that we are devoting most of our time. So yeah, thank you for your attention and I'm happy to take questions.
Okay, we are already starting with the questions.
Thanks for the talk, Rafael. I have a question which may... Everything rests on the fact that the causal structure is a directed acyclic graph. What happens if the graph is cyclic instead?
So yeah, that's in a classical setting, this doesn't happen. Like you run into paradoxes if you do that. Like I guess you can even model like the grandfather's paradox using that. Like it's like cause being its own effect and this sort of things. So if you want to model something more more complex or more dynamical than that, there are other tools to be used, like for time series and this sort of things. But in the end of the day, like you can always map back this to a DAG, like a more complicated one. But in quantum physics, you can do things more interesting, right? So there is this part of the quantum causality community that look at superposition of causal orders. So this is something that you can go to the lab and actually verify, that it's the idea that, so now you could have a superposition of a qubit 0 and qubit 1, spin up and spin down, but what about the superposition of A causes B plus B causes A? So you see, you cannot represent that with a DAG, because if you try to make a DAG, you have an arrow from A to B and another one from B to A, so it's cyclic. And to exactly like accommodate this sort of things that happen with quantum physics, like this superposition of causal orders, and many people like doing quantum gravity. This is well beyond my knowledge, but I know that they are starting to look into this sort of things. So there is a new tool that it's called the cyclic DAGs, that are tools that allow you exactly to model this sort of superpositions. I don't know much about them, but they exist.
More questions? Yeah. No. Wait.
So maybe I missed the point, but what's really the consequence of the fact that the double-slit experiment has a classical explanation?
That the double-slit, well, for me to disagree with Feynman. But no, I mean, it's like if you take like a course, an underground course in quantum mechanics, I think the first lecture is going to be, look, this is very weird. This is very quantum. Like nothing can explain that, and that's not true. So what I think my main message with this double-slit being classical is that we should take care of what we define as non-classical. Like it has an explanation if you allow your ocean of explanations be a bit larger. So we are not talking about any specific physical theory. I'm not talking about electromagnetism or classical or Newtonian physics. I'm talking only about probabilities and causal structures. And with this very general, very broad way of modeling physical systems, I can see that actually it has a classical explanation.
Regarding the debate between different interpretations of
Please repeat the question.
So he's asking about the different interpretations of quantum mechanics. So, like a good interpretation should be indistinguishable from a standard quantum theory. So, in principle, there is no way that any of that will tell you anything about different interpretations. Well, okay, so like if you can use these DAGs to maybe clarify what a given interpretation says. So if you go to Bell's theorem, right? What Bell's theorem tells you is that, so this book here, it's very nice, I recommend it. So where is Bell? Here. So what Bell says is that the causal structure of this kind here is not going to be able to explain what you obtain with quantum mechanics or what you obtain from the experiments. But if you relax some of these assumptions, for instance, you could relax the locality assumption. You could say, well, independently of two things being on opposite sides of the universe, somehow what is happening on one wing is affecting what's happening on the other wing. And this is exactly what happens in Bohmian mechanics, right? You give up the locality assumption with this pilot wave and these sort of things. But, so these DAGs, they kind of clarify that, but in the end of the day, the predictions of both theories, because they are interpretations, they should be the same.
More questions?
First of all, thank you for the talk. I have a naive question. What happens now if I apply this quantum classic, this quantum causality, this quantum causality in the case of the Bell scenario?
Yeah, so here, like, I'm applying classical causality to understand it. And I can also say, well, like, so classical causality is not enough. I get something that it's incompatible with my notion of causality. So I have to generalize it, right? So people came up with the idea of quantum causal models. And you have different ways of defining what a quantum causal model is. But the basic difference is that now, instead of treating the causes as, like these common causes, as random variables, you treat them as density operators. And this changes everything. So, like, you have a well-defined notion of a quantum causal model. And this is important, for instance, when you talk about post-quantum theories. Now you could say, like, okay, how could I possibly prove quantum mechanics false? So I have a quantum causal model now. This quantum causal model will define a new set of Bell inequalities that are quantum Bell inequalities. So something like that, I mean, it's actually very simple. Like, if you go back to Bell, this here, it's a classical Bell inequality. So this bound of 2 is valid for classical models. If you have a quantum causal model, you can prove that the most you can get here is 2 square root of 2. Anything beyond 2 square root of 2 would be something beyond quantum mechanics, like a post-quantum theory, right? So if you would violate experimentally this inequality with epsilon here, you would be proving that quantum mechanics is wrong. I don't believe that this is the case, but I mean, in principle, you could test that. And this is one of the reasons why people care about quantum causal models. Like, it's a model now where you combine causality with quantum theory. And then you get, like, this sort of bound here.
Okay, thank you.
More? Okay, if not, we can thank Rafael again.